Episode 8. Title of the Radio Enable Learning course is Energy Physics. Unit 2. Estimation of energy and power in a double cycle system. In a double cycle system, the estimate of energy and power can be made as per usual calculation of power in hydropower plant, considering the average discharge and available head at any instant. Then total energy can be obtained by integrating the value of instantaneous power. The energy that is available for a tidal plant depends upon the range of tide and volumetric capacity of the basin. The power from the plant is generally obtained in parts in during of 3 to 3.5 hours in a flood tide cycle and for equal duration in an ebb cycle. There are approximately 705 full tidal cycles in a year. The power or total energy is first calculated per tide cycle, and then yearly total energy generated can be obtained by explain the following expression. Let capital V be the volume of the basin. Capital V equal to capital A H naught. A is the average cross-section area of the basin in meter square, and H naught is the difference between maximum and minimum water levels. Average discharge capital Q is equal to capital A H naught divided by small t. Small t is the total duration of generation in one filling emptying operation. Now power generated at any instant capital P equal to rho capital Q H divided by 75 into eta naught HP. That is also equal to rho Q H divided by 75 eta naught into 0.736 kilowatt, where rho is the average density of the seawater, that is equal to 1025 kilogram per meter cube. Small h is available heat at the instant. The total energy is equal to integration over 0 to t capital P dt. That is also equal to integration over 0 to t rho capital Q H divided by 75 into dt into eta naught into 0.736 kilowatt per tidal cycle. Then yearly power generation is equal to integration over 0 to t rho capital Q H divided by 75 into dt into eta naught into 0.736 into 705 kilowatt hour per year. The available head small h is function of time, and integration over 0 to t h dt can be obtained graphically. Next we move on to site requirement. The utilization of tidal energy requires construction of a barrier across a narrow inlet to an bay, thus forming an enclosure or basin in which ocean water can be impounded. Electricity can be generated by allowing water to flow through a turbine from the basin filled at high tide to the open ocean during falling tide, and also the basin is being filled from the ocean during rising tides. In each case, the maximum amount of electric energy that can be generated depends on the product of the tidal range capital R and the mass or volume of water flowing through the turbine. The volume is equal to the range multiplied by the area of the impounded water. Hence the electrical energy is proportional to the square of the range and the area of the enclosed basin. The favorable site for a tidal power plant should then have a large tidal range, and the geographic features should permit enclosure of a large area with reasonably short dam or other barrage. Next one is storage. Storage is necessary when the alternative electricity production schemes are not or cannot be connected with the electrical grid. Tidal power plants are not exemption to this rule. There is a strong case for associating them with storage to provide for the varying needs of the consumer. Also taking into account evenly presence close by of other plants. The tidal power plant has, by its very nature, many of the components required of a pumped storage scheme. It has also the advantage that with such a scheme, added tidal power becomes a firm day time source of power. This is important because of the principal saving provided by a tidal energy is that of fuel, probably also of pollution abatement costs. The fuel saved depends on the type of plant whose load factor is reduced and how such plants perform with the addition of tidal power or without it. Evidently, this argument applies only to high development countries where there are numerous other plants and for less and to developing countries. The alternate to storage when energy is available, that means but power is not needed because of timing, is not to generate but the potential thus left untapped is not recoverable at a later time. It is pretty much a case of store it or you will never have it when needed and no potential is available. Hence, the extra capital investment may be justified. For tidal power being produced in mechanical form, only batteries, compressed air and hydraulic storage can be considered. Flywheel could be used but its technology is not yet ready. Next one is flywheel storage. By connecting flywheel to motor or generator, it is spin up to high speed and absorbs energy. This energy can be returned to the motor generator by decreasing flywheel speed. However, only small quantity can be stored and they are limited to short period of time. Next one is battery storage. Perhaps most flexible and practical are electrochemical batteries. These batteries are the most common, but research is being conducted with less expensive and lighter types. Also presently available are aqueous solution nickel and nickel cadmium types, but there are much more costly. Again, this type of storage is suited to small plants, particularly self-containing ones. Next important type storage is hydraulic storage. Hydraulic, that means pumped water storage, is mostly frequently mentioned in connection with tidal power plants. Two reservoirs at different elevations are linked by pumps and turbines and their motors and generators. They constitute the accumulator, that means a reversible pump turbine connected to motor generator achieves the same result. Off-peak energy which could be used is put to work to pump water from the lower into the upper reservoir, which can be run through the turbine and generator and provide energy when needed at a later time. Power can be provided immediately on demand. Reservoir must be found or built, of course, and a certain amount of energy is lost to active and work the pump. Next one is compressed air storage. This is also an important storage device. Air is compressed during off-peak period and thus the stored underground. It can then be called upon the work gas turbines and provide electricity. Tidal energy can be used directly to drive air turbo compressor. Next one is advantages and limitations of tidal power generation. First, we will discuss about advantages. The biggest advantage of the tidal power is, besides being inexhaustible, it is completely independent of the precipitation. That means rain and its uncertainty. Even a continuous dry spell of any number of years can have no effect whatsoever on the tidal power generator. The tidal power generation is free from pollution as it does not use any fuel and also does not produce any unhealthy waste like gases, ash, atomic refuse. The next one is, these power plants do not demand large area of valuable land because they are on the bay, only seashore side. Next one is, peak power demand can be effectively met when it's worked in combination with thermal or hydroelectric system. Next, limitations of the system. There are a number of reasons why the tidal power generator is still a novelty rather than a normal source of energy. The reason can be discussed as follows. The fundamental drawback to all methods of generating tidal power is variability in output caused by the variation in the tidal range. The tidal range is highly variable and thus the turbines have to work on a wide range of head variation. This affects the efficiency of the plant. Since the tidal power generation depends upon the level difference in the sea and the inland basin, it has to be intermediate operation feasible only at a certain stage of the tidal cycle. This intermediate pattern could be improved to some extent by using multiple basins and double cycle system. The tidal range is limited to a few meters, thus the bulb turbine technology was not well developed. Use of conventional Kaplan runners was the only alternate. This was found to be unsuitable. Now with the development of reversible flow bulb turbines, the difficulty in overcome. The duration of power cycle may be reasonably constant, but its time occurrence keeps in changing, introducing difficulties in the planning of the load sharing every day in a grid. This handicap can be removed now with the help of computerized programming. Seawater is corrosive and it was feared that the machinery may get corroded. Stainless steel with a high chromium content and a small amount of molybdenum and the aluminum bronsons provided to good corrosion resistance at Lawrence project. The vinyl paint exhibited good results. Construction in sea or seashore is found difficult. Cost is favorable compared to the other sources of energy. It is feared that the tidal power plant would hamper the other natural uses such as fishing or navigation. Next, we will discuss about advantages and disadvantages of wave energy. The wave energy has the advantage over wind or solar that the energy has been naturally concentrated by the accumulation over time and space and transported from the point at which it was originally present in the winds. The degree of power concentration affected by waves is quite substantial, whereas the power density in the wind may, at a good site, average some hundreds of watt per square meter. Wave from being transported across a plain perpendicular to the wave propagation direction at a good site is from 10 to 100 times at large. It is free and renewable energy source. Wave power devices do not use up large land masses unlike solar and wind. These devices are relatively pollution free, and because they remove energy from the waves, leave the water in a relatively state in the waves. The most important disadvantages are the major disadvantages of wave energy as compared to wind is that the energy is available on the ocean. The extraction equipment must operate in a marine environment with all that implies in terms of maintenance, construction cost, lifetime and reliability. The energy may have to be transported a greater distance to shore. Wave energy converters must be capable of withstanding very severe peak stresses in streams. There is relatively scarcity of accessible site of a large wave activity. Wave energy conversion devices that have been proposed are relatively complicated. Economic factors such as the capital investment, cost of the maintenance, repair and replacement, as well as problem of biological growth of marine organisms are relatively unknown and seems to be on the large side. Then we will discuss about the small hydropower potential, which remains largely untapped so far because of an impression that first one is small hydroelectric project entail higher capital costs or per kilowatt installation basis, higher managerial and administrative costs, relatively low utilization, unstable operation of isolated system due to low inertia, certain problems caused by the dispersed nature of projects in site identification, preparation of reports, proper construction planning and management of operation, etc. Yet one cannot deny a place for small tidal in the large energy framework, primarily because small or mini hydropower, that means SHP, is a non-conceptive generator of electrical energy utilizing a renewable resources which is made continually available through the hydraulic cycle of environment. Small hydropower SHP is essentially non-polluting and release no heat. Environmental impacts are negligible and for small installation may be totally eliminated. With the development of compact, efficient machines, the investment per kilowatt installed is not very high. SHP projects do not require large capital investment. Compared to other conventional energy generation schemes, these projects have low gestation period ranging from 8 to 24 months. Operating costs are low and the equipment does not need trained and skilled personnel. With the introduction of microprocessor, the SHP stations may run virtually unattended. Further freedom from fuel dependence together with long life of SHP plant make installation resistance to inflation. SHP is ideal decentralized energy generation source. It can supply energy to rural feeders, thereby cutting distribution losses to large extent. SHP can be synchronized with grid and has been demonstrated in national demonstration project in Himachal Pradesh, Haryana and Tamil Nadu. SHP synchronization with utility grid improves voltage profile. With the interconnection and synchronization with grid, plant utilization factor become very high. Thus, SHP becomes economically attractive. Due to their small size and local availability of utility grid, SHP stations generally use induction generators. Thus, the induction generator are not only inexpensive but also the problem of synchronization and interconnection is also vastly simplified. SHP can be catalyst in remote areas using relative simple technology in mobilizing productive resources and cutting enhanced economic opportunities for local residents. Most of these schemes in India can be constructed on existing canals and irrigation systems, thereby necessitating minor modification and result in minimum disturbance to surrounding environment. SHP can be developed and hydropower capacity at existing irrigation dams and powerhouses. The possibility of retrofits and additional turbines and generators make upgrading of present installation attractive. The determinants in the economic feasibility of alternative proposal of power generation may not necessarily depend upon the variables of the highest gain from the individual scheme, but variables on the basis of the impact on economic of the system as whole. From the consideration of high efficiency and low cost per kilowatt capacity, a large set may be individually more economical, but this individual economic gain might outweigh by the adverse economy as consequence of low operation efficiency due to partial loading, sudden loss of unit, longer gestation period due to sizable difference between the generation capacity of the unit and increment rate of load development in the region served by the plant. Transport difficulties in hilly areas, transmission losses, transmission costs, high cost of fossil fuel when compared to thermal power. In coming years, the small, that means mini, micro and small, shall be more feasible and economical than other sources like thermal power because cost of fossil fuel. Now we conclude the unit 2. It has been concluded a campaign should be made to give proper publicity for funding out the maximum mini, micro and small hydroelectric generation sites on the following grounds: that mini, micro and small hydroelectric power is a new source of renewable energy. The mini, micro and small hydroelectric is an alternative way of developing hydroelectric resources of a country. It can develop the same potential as would be available for normal scheme. That mini, micro and small hydro potential is more economical, that it saves fossil fuels, that it reduces the transmission losses, that it is suitable for isolated loads, that it is easy to operate, that it has low gestation period, that it is equipments can be standardized easily. Next we will discuss about some important questions of unit 2. What is the basic principle of ocean thermal energy conversion, OTEC? What are the main types of OTEC power plants? Describe their working in brief. Next one is describe the closed cycle OTEC system with its advantages over open cycle system. Next one, explain with sketches the various methods of tidal power generation. What are the limitations of each method? Next one is, what are the difficulties in the tidal power development? What are the advantages and limitations of wave energy conversion? Next one is, write a short note on wave energy conversion machines. Write a short note on small head hydropower development. What type turbine is best suited for micro hydel plant? Describe it. Next one is, describe the different types of turbines are in use for small scale hydroelectric plant. What are the advantages and limitations of small scale hydroelectric power generation? Thank you.